Well, welcome to class, everybody. Got another minute or so, and then I'll start. You guys are all doing well on the quiz. We've got another couple minutes, a couple of people still finishing up. Andy definitely killed this quiz. He did it in 14 seconds and got a perfect score. Way to go. Not that it's a speed test, but that is impressive. So you get the award for speed today and accuracy, which is actually something we'll be talking about today. So yeah, today we're going to be talking about the software quality landscape. And so I have this nice little landscape here just to get us to feel landscapey. And, and so you guys have read it. And the thing is that this chapter starts out talking about the fact that testing isn't the best way to find errors. We've already talked about that in several other aspects in this class, right? Taking more time to code can actually increase the number of errors. And so that's why I mentioned what I mentioned about Andy and the speed of the quiz. Sometimes faster isn't, sometimes slower, taking it slow is not always better. In fact, it turns out that you can go too fast, but you can also go too slow. And generally speaking, though, development work that's done, quickly and efficiently also tends to be higher quality. And it turns out that there's no single silver bullet to writing perfect code or writing better code, right? It turns out that you can't say, well, this is the thing that I do, right? There is no such single thing. Developing quality code is a composite of many, techniques. And so we're going to be talking, I'm not going to read through these, but we're going to be talking about what is it that makes software have high quality, and what does that even mean, right? And so the first thing that we can think about is the fact that the qualities of a piece of software can be either internal or external. And the external qualities are the things that the users notice, right? In other words, a user notices if something runs really slow, or a user notices if they have to buy more memory because the computer takes so much memory that they have to buy more, right? The user notices clearly if the system crashes or if it gives the wrong answers, right? These are things that the user actually cares about. The internal qualities are things that the programmers care about, right? And that the users will never know about. And so we have these lists, and I'm not going to read through these because I'm going to go into them in more detail, but we have a bunch of things that the external world cares about and a bunch of things that the internal people, the programmers and the software developers and the companies that are making the software care about. And of course, one of the most obvious is correctness, right? So if somebody's using software, they want to know that it actually produces the right results at the right time. And so we call this, again, what we're doing is we go through these just to make sure we see the big picture. we call software quality a landscape because it's not just a simple thing. It's a lot of things, right? And we're going to talk about all these things, and we're going to say, well, not only, well, of course, we'd like to have all of these things, but we may not be able to have all of these things. In fact, sometimes these things are in competition with each other. For example, correctness and robustness, sometimes you can't have both. And so you have to decide, which one would I rather have, right? And we've actually talked about that in the past. And so we have to pick, we have to choose a landscape. We have to choose what we want our software strengths to be. Now, of course, if we don't choose at all, we're probably going to get crap. And so part of the process is to ask ourselves, of these qualities, how important are they? So how important are perfect answers, right? You know, if this is software dealing with financials, probably correctness is really important, right? If this is a search engine for information about Pokemon, probably correctness isn't that important. Maybe user experience is more important, right? Usability, right? This has to do with how easy it is for the system to use. Efficiency, how well the system uses system resources, right? So you like a program that runs quicker, or that doesn't, you don't have to upgrade your computer just to run it. Reliability. Does it work all the time, or does it occasionally fail? Integrity. Now that's an interesting term. What is integrity? Integrity is really two aspects of integrity. One is security, right? A system has integrity if unauthorized users or robots or whatever can't get in there and mess it up. That's a type of integrity. Another type of integrity has to do with consistency and what's the word I'm looking for? Coherence, right? So if you're working with a really complex system that has multiple databases, not just tables, but maybe multiple databases that are spread across multiple geographical locations, integrity might mean consistency, right? What happens if in this big heterogeneous system, some of the systems are saying one thing and the other ones of the systems are saying other things, right? So if you have a big e-commerce system and it's complicated and it's spread across lots of servers, a lack of integrity might be a situation where some of the servers think something costs one thing and some of the other servers think it costs something else. That's inconsistent. That doesn't make sense. That's a lack of integrity, right? Now, you may or may not care about that. You might say, well, I don't care if some people get different prices, but you may really care about that a lot, right? If you're writing an online bidding system, you probably care about integrity in the way that people perceive it, because people aren't going to be happy if they bid on something and because of the timing and the lack of consistency within the system, somebody else wins the bid even though they had a lower bid. Adaptability. So this has to do with this: if you buy a piece of software, can it adapt to multiple situations, or is it rigid? You may want it to do this, you may not want it to do this. All of these things you may care more about or less about. Accuracy. Now, accuracy is the degree at which a system is built is free from error, especially with respect to quantitative outputs. Okay, so this differs from correctness. It's a determinant of how well a system does the job it's built for, rather than whether it was built correctly, which is a subtle difference. And sometimes it's hard to understand, but correctness is mainly about, did you build it the way that you wanted it to be? Okay, Now, maybe you didn't want it to be the way, maybe it wasn't the way you built it, wasn't the way, was the way you wanted it to be, but it wasn't the way the person who uses it wants it to be, right? Because we talked about this at the very beginning of the class, what our idea of what the customer needs and what the customer actually needs are maybe different things, right? So the software may be perfectly correct according to our specifications, but it may not be what the user really wants. And so accuracy is, does it actually do what the user really wants? You see the difference? Then we've talked about this last one, robustness. I think it's the last one, yeah. This is basically how well does a system perform under either with bad inputs or stressful environmental conditions. Bad inputs could be stuff you type in, but it could also be it goes to read a file and the file's corrupt, or it tries to get something out of the database and the database is down, right? Or it tries to connect to another server and that server is down, or there's communication breakdowns, right? A connection is down. You know, how well does it perform, right? A kind of a simple example of that type of robustness is Kenyon actually has 2 internet providers. 2 separate companies have lines coming into Kenyon with which they provide internet service. Now, they could have just doubled the amount of service from one company, but if that company had a problem, then they'd have no internet service, right? By splitting their service among multiple companies, they make their system more robust. 2 different companies have to fail before the internet goes down, right? That's robustness. We see this, by the way, in server systems. If you look in the server racks where computer servers are at, virtually all servers have multiple power supplies and multiple storage systems, so that if one fails, it just keeps right on going. They even oftentimes will have multiple memory systems that are clones of each other, and so you can actually lose memory chips while the system is running, and it will continue to run, and you'll never notice the difference, right? That's robustness. Okay, internal software quality, right? What programmers care about is, did I write a program that I can maintain, or is it so convoluted and badly commented and horrible variable names and inconsistent methodologies used, I can't maintain it. I can't figure out, I can't go back to it and fix it or add new features. Flexibility is the ability to which systems can adapt. You can adapt it for other uses. Like, for example, you make a class, and if you make a flexible class, you might be able to reuse it. If it's really rigid in what it does, you might have to say, well, I got to write a new class now. We care about portability, right? Probably a real obvious example of portability is you build a system to run on Windows. Can you also make it run on Mac OS or on iOS or on Android, right? Reusability is the ability to take stuff in which you've written parts and pieces or wholes and say, hey, I can reuse this in another system, right? This can save you a lot of time, not just in terms of writing the code, but every time you write code, then you have to refine it and debug it. And if you've done that once, it's really nice, right? The software template library in C++ are highly reusable templates that people have spent a lot of time, testing, and you can be pretty sure they're not going to have an error in them because everybody uses them all the time. Readability. We like our code to be readable, right? That's an aspect of internal quality. We like code to be testable. how is it that we can design code to be testable versus not testable? Any ideas?
You want it in like chunks and like functionally separated so that you can test each function on its own rather than wondering where problems that you run into are coming from?
That's great, right. So if we can take our code and break it down into pieces that can individually be tested and then assembled, that's a type of design that makes things more testable, right? You know, another thing we can do is we can actually build into our code things that we can turn off and on, right? We talked about that when we talked about asserts, remember? If we put asserts in there, we can enable the asserts, and then when the asserts are enabled, we can test it easier, right? If something breaks, we can say, well, turn on the asserts and let's see what's going on, right? If you don't have that, you're like, well, I don't know what to do next, right? It's a little bit harder. So you can actually build in, you know, stuff into the code that actually makes it testable. Understandability, right? Is the system designed and organized in such a way that you can understand it? We've talked about this a lot, right? This is what classes and functions are all about, right? If we design a function, a system well, we compensate for the fact that our brain can't understand big complex things because we only have to focus on pieces of it at a time. And so this is huge, right? So it turns out, and I'm not going to spend a lot of time talking about this, but it turns out that when we focus on one external quality, it oftentimes affects other ones, right? So for example, if we improve correctness, we also improve correctness because it's the same thing. Doesn't really change usability. Correctness can also help improve reliability and efficiency and accuracy, but it turns out that making something perfectly correct can have a detrimental impact on robustness. Because if it's either going to be correct or not function, it's not very robust, right? So we might want to have a system that's not always correct all the time, but it's close enough. It's close enough to keep you going, right? And so again, we can go through all of these and see how choosing one has an effect on another one. And so the point is if you're going to build a real product, a real professional product, you want to sit down and you want to think about, you're thinking about the landscape when you think about this. You're saying, what are the things that are going to be important for us in this domain, right? If we're writing the code for a heart pacemaker, they're going to be different than if we're writing a code for a new video game, right? Or if we're writing the code for a banking system, or we're writing the code that controls the steering system on a car, right? All of these have different sorts of you know, the code itself has different sorts of impact on the users, and you have to determine what is the user actually going to care about. And then you focus on those. And so just saying, I'm going to write the best code ever is not enough, right? Developing code is complicated by the fact that you have to figure out what kind of code you want to build. So this whole concept that we call software quality assurance is something that companies do, and this is a planned and systematic program of activities designed to ensure that the system has the desired characteristics, right? So if you're going to build a system, you first have to decide what are the characteristics that we care about most, and then you have to come up with a plan for achieving those goals. You can't just say, well, we hope that it's correct, but we're going to try really hard when we're writing it to make it correct or robust or whatever, right? And how do you do that? And the answer is you focus on the process rather than the products, right? So when you build something, you don't think about the final product so much as you think about what processes do we use. Let me give an analogy. Let's say you're going to build a house, right? Now, let's say you want this house to be very energy efficient, right? Well, then you're probably going to have processes that are going to be involved where you're going to say, okay, we're going to, for every time we put a board up, we're going to seal it so there's no leakage, right? And so there's processes that you do. You don't just slap up a board. You put a board up and you go through the process of sealing it. And you say, we're always going to do that everywhere. Everywhere where there's a joint, we're going to take time to seal that joint as we're building it, right? And so you think about these things as you're working. And you can do the same thing in code. You can have certain processes that you go through, right? And there's different sort of processes, like a code review is a process. Naming variable names consistently is a process. Having commenting standards is a process. So the idea is to have when you build software, is to have an explicit set of quality objectives among the external and internal characteristics. Without explicit goals, it's a shot in the dark. You have to sit down and say, these are our goals, and these are the processes that we're going to use to assist us in achieving those goals. And these are the measurements and the tests that we're going to use to determine whether we actually did hit that goal, right? So it takes planning, it takes testing, it takes evaluation to meet specific goals or objectives. Now, one aspect of this is a testing strategy, right? How do you test things so that you're more sure that it reaches the objectives that you've decided are important? Well, you're gonna have to sit down and say, okay, we want robustness. What sort of tests are going to be required for robustness? Maybe you'll say, well, let's try to overload it with too many users and see if it crashes or if it just slows down a little bit, right? How does it respond in that situation? Or let's see what happens in a case where lots of people are typing in bad information, right? And so you come up with tests that do that, and then you see how it responds. When I used to write network drivers and protocol drivers for wireless, I wouldn't just say, okay, let's transfer a file through it and see if it works. I'd say, what happens if I've got, 10 different communication streams absolutely maxed out simultaneously? What happens? And let's do that for days at a time. However, testing isn't sufficient alone. It turns out that testing can only do so much. And so one of the things that we do is we develop guidelines for activities that we're going to participate in that we have shown to improve software quality. One of these that we've talked about before is informal technical reviews, right? Sitting down and looking at each other's code informally and saying, look at this that I wrote. What do you think? Is there a way I could have done it better? Do you see any errors I might have missed? Then there's formal reviews where you literally do the whole thing where you send out the code, everybody looks at it in advance, they come into a meeting, and then they talk about it, right? External audits. Sometimes companies have part of the contract says another company's going to come in and audit your code. They're going to look at your code and then they're going to write up a report. These sort of things happen in all sorts of industries. Right now, Kenyon is has to be reaccredited every 10 years, and we're getting ready to go through a new accreditation process. Well, people come in from other colleges and they study us and they look at everything. And so we have to write up all these reports and put all this information together so that they can study us and determine whether or not we deserve to be accredited. That's an external activity. Some of the processes that are important for quality are change control procedures. What are change control procedures? You ever hear of anything like that before?
Like having a set of steps that all the coders follow when they're ready to make a change to the code.
Right, right. So you of course early on you come up with specifications for what you want to build, and you design and you say this is what it's going to do. These are the modules. These are the interfaces. These are the components, right? And then sometime in the middle of it, oftentimes you're going to have a situation where somebody says, well, you know, this maybe isn't the right way to do it. We've discovered something and we think there's a different way to do it. Or we want to add this feature, or we think we should remove this feature, right? It's very important that there's a process for doing that, because oftentimes individuals or subgroups will see something and they'll say, well, I don't think that's the way to do it, because they don't see the bigger picture, or they don't see what other people are doing and how the impact of their change is going to impact other people. And so it's very important that there's a process you go through so that everything is correctly vetted at every level, so that changes don't occur that are later on you're going to find out, uh-oh, we didn't realize that. Now we're totally screwed. Measurement of results, right? One of the big things you have to be able to do if you're going to achieve certain qualities is you have to come up with strategies for measuring and evaluating whether you've actually met those. How do you know if a system is correct? How do you know if the system is efficient? How do you know if a system is robust? Can you come up with tests or other metrics whereby you can evaluate how close you've come to meeting or exceeding those quality desires? Now, one of the things in the development process that can be huge is prototyping, right? If you're not sure what the customer needs, or if you're not sure how something is going to work, you go ahead and mock it up very quickly and build something just to show people, or just to experiment with, and then you learn what you need to learn, rather than putting all your eggs and saying, well, this is what we're going to do, and we're just going to push through until it's done. And, you know, then it doesn't work right. So setting objectives. So for each objective, you have to have a plan of how you're going to achieve that. Now, it turns out that, again, here are some different objectives the team was told to opt. Like, for example, minimum memory use, then that's number one. So then maybe most readable output and most readable code isn't as important, right? Minimum programming time maybe is least important at all. Output readability, maybe we don't care so much about memory, but now we care about readable code and readable output, and so on, right? You can see this is like a landscape, right? We're making choices, and choosing one thing to be important, like the least amount of code, means maybe we don't care about, or we don't optimize for some of the other things. Relative effectiveness of quality techniques. If builder built buildings the same way programmers wrote programs, then the first woodpecker that came along would destroy civilization. Hopefully we're better than that, but I think we're in the process of becoming better. So some practices are better at deflecting defects than others, and different methods find different kinds of defects. In fact, here's a very interesting table. Now, what this is all about on the left, removal step, is a mechanism that you use to try to remove defects. And then this is part of a study, and they found that the lowest rate of finding defects of each and the modal rate and the highest rate. So what this is all about is how effective are each of these methods. So in formal design reviews, the review, on average, more or less, about 35%. But the highest they can reduce is 40%. In other words, the best you can do, if all you do is formal design reviews, you're only at best going to get rid of 40% of the defects. Formal ones do a bit better. This is design reviews. Code reviews, informal code reviews, formal code inspections, does pretty good. Modeling or prototyping, very helpful. Personal desk checking of code, moderately helpful. Unit tests, new function tests, integration tests, regression tests, system tests, low volume beta tests, less than 10 sites, high volume beta tests, greater than 1,000 sites. Now, which of these is the one that gets all the errors?
No one.
No one, right? So that at first might be discouraging, but the whole idea is what? You use more than one, right? If you do all of these things or some set of these things, each one of those comes into play, and collectively we're going to get closer and closer to 100%. One way to think about this is think about slices of Swiss cheese, okay? A slice of Swiss cheese has holes in it, doesn't it? Imagine those holes are like errors, right? And so you lay that down on the table, and you consider an error if you can see the table. So you lay this one piece of Swiss cheese down. It doesn't cover everything because it's got holes in it. You lay another slice. It's got holes in different locations. Some of the holes match and some of them don't. So there's less holes, right? If you keep layering more and more slices of Swiss cheese, eventually there's not going to be any holes, right? Because you're going to cover up everything. You see the concept, right? And so that's kind of what you're doing here. So modal rates don't rise above 75% for any single technique, and that the techniques average about 40%, right? Now, it turns out that typical organizations often use test-heavy defect approach and achieves only 85% of defect removal efficiency. Leading organizations use a wider variety of techniques and achieve defect removal efficiencies of 95% or higher. So we need to use a combination, just as I've been talking. Actually, I think I'm going to skip this one for now. So the cost of finding the defects, right? So not only do we want to think about just the impact of, the reliability of certain methodologies of finding errors or defects, we want to find out how much they cost, right? Because some may be really expensive and some may be really cheap. And so we should probably always do the cheap ones, right? Because if they're cheap, let's just do them. The more expensive ones, we may have to decide if it's worth it, okay? One method that isn't talked about here is formally proving correctness. You can actually do this. It's not something that's ever taught at an undergraduate level. It's very complicated. But you can actually, for small systems, you can actually write formal mathematical proofs to prove something is correct. It's really hard to do this. It takes a huge amount of time. And you know, it's exponential. The bigger the system, the more time it would take, right? You could proving that an operating system is correct. Like if you wanted to prove Windows 10 is correct, there's just not enough time in the universe to do that formally. Okay. So we want to know what the cheaper areas are. It turns out that inspections are almost universally cheaper than testing. Because think about it, when you write tests, this is sort of intuitively should make sense. So when somebody's testing code, have you ever, you know, so let's say somebody gives you a program to test and you're not the writer of it, you're just the tester of it. What do? You write it, run it, and run it, and run it, and run it. Then you see an error, and you write that down. Run it, and run it, and run it, you see an error, right? And so you're just kind of taking shots in the dark, right? It's kind of the equivalent of, you know, shooting at a target with a bow and arrow with your eyes closed, right? You don't know where the target is, so you're just kind of randomly. Now you can do a little better than random, and we'll talk a little later about testing, but it, you know, testing, you don't know where the errors are, and so you're just poking around trying to find it. Whereas when you do inspections, you're actually looking at the code, and you're saying to yourself, is this code right? Or does this code have a defect, right? That turns out it's much cheaper to do that. But people don't want to do that, right? People want to test. They want to write code and then they want to test it, right? It's kind of like driving a car, right? You would rather drive the car than spend time looking at the engine. Or looking at the suspension system, because it seems like you're getting something done, but it actually is better to do inspections. So these guys found that the cost 6 times as much to detect design defects by using testing as by using inspections. Because just think about design defects. Design defects means you came up with the wrong design, then you wrote code for that design, and then you found out there was an error. The cost of fixing that is huge because it's not just a coding error, it's a design error. Oftentimes you have to go back and almost completely rewrite your code. So you don't want to catch those errors during the testing phase. You want to know that it's a problem before you even write the code. So in general, the time between making the error and catching the error, the longer that time is, the more expensive it becomes to remove it. Just like I was just saying, a design error gets made early. Finding that error, for example, after you've completely written the whole system, can be catastrophic. It's catastrophic. Microsoft's application division has found that it takes 3 hours to find and fix a defect by using code inspection, a one-step technique, and 12 hours to find and fix a defect by using testing, a two-step technique. Effective software quality program must include a combination of methods, just like we've talked about. Formal inspection for all requirements, all architecture, and all designs. Those things that are done early on, the requirement setting, the architecture for the system, and the designs for the critical parts like the classes and objects. Before you actually code, those decisions that you make are huge, right? Heaven help us if we don't even do a design and we just start to write code, then we're hopeless, right? But we want to do all of these designs, and then we want to check them carefully before we even write our first line of code. Another quality technique, again, that we talked about was modeling or prototyping, right? Building a model of what we're going to build, building a prototype and trying things out and seeing what happens and finding out what we learn and seeing whether or not it's what people really want. You know, the worst possible thing is if you build a system and you deliver it and people say, well, this seems to work right, but it doesn't do what I need it to do, right? It doesn't have any errors in the code. The error is in the design. You didn't design it right. you missed certain features, and maybe adding those features is impossible at this point without completely rewriting the software. So by producing a prototype and letting people talk about it, try it out, you learn what it is that that person actually wants. Okay, what this really gets down to is the fact that people don't usually know exactly what they want, or they don't know how to say it, right? So you say, what do you want? And they're like, well, I don't know. I guess I want this, that, and this. And, they may miss something because they don't know exactly what the machine can do for them. In fact, sadly, but true, a lot of people's understanding of what they need is of the form of, quote, I'll know it when I see it, right? You ever heard that term? I'll know it's right when I see it, right? Well, how are you going to do that? You don't want to build a whole system and they say, well, I know what I want, and this is not what, I don't really know exactly what I want, but I do know that this isn't it. Then you're like, oh crap, right? But if you build a prototype, they can say, okay, these are the things that make sense to me. These other things, I don't think I want that, or I don't want it to work like that. Other quality techniques, code reading and inspections, we've talked about that, and then actual execution testing. So when do we do this thing called quality assurance? Now, it turns out that defects creep into software at all stages, from proposing to prototyping, all the way to the final integration, and even testing itself can have a defect, right? You could have bad tests. Everything can have a defect. Consequently, you should emphasize quality assurance work at the early stages and then continue it throughout the rest of the product, right? If you want a good product, you have to maintain these vigilant processes of quality assurance throughout every aspect of it. So it's planned into the project as the work begins, right? You literally plan for quality. So it should be part of the technical fiber of the project as the work continues. It should punctuate the end of the project, verifying the quality of the work as the project ends. So quality assurance is this permeation of these methodologies throughout. So the general principle of software quality. This is something that many people miss, right? Improving quality reduces development costs. It's the old adage of, you think it's cheaper to just do something quick and dirty, right? Say, well, I can just, I want to save money, and so let's skip the design and let's just start writing code. Let's not spend time talking about quality. Let's just work hard to make quality, right? All of these notions, these intuitive notions, are wrong. We don't save cost by skipping things. We save cost by doing things right. Because when we skip these things, we make errors and things get worse and worse, and we end up having to redo things over and over, literally. So this is a very important general principle. And this is why for us, you guys, it's just programmers who are learning, it pays to take time to do your homework before you try to write a piece of code, right? It actually saves you time in the long run. Now, here's an interesting aspect of this. Listen to this carefully. Software projects with the lowest levels of defects had the shortest development schedules and the highest development productivity. Software defect removal is actually the most expensive and time-consuming form of work for software, right? So having things all spread out and saying, we're just going to give ourselves lots of time to write code is not necessarily the best solution. In fact, it's not the best solution. It's better to do things quickly and efficiently, but do it with quality in mind throughout all the processes. In 1985, 166 professional programmers wrote programs for the same exact specification. The resulting programs averaged 220 lines of code and typically a little under 5 hours to write. The fascinating result was that the programmers who took the medium time to complete their programs produced programs with the greatest number of errors. Look at this. So, isn't that a surprise? Isn't that counterintuitive? So the number of defects were the lowest. Now, it turns out that people who took a really, really, really long time didn't have very many defects, probably because they were just really careful in everything they did, but they took so much time. The person who did it the fastest actually didn't have very many errors either. It was these people who were in the middle. Wow. So I think that's it, right? So when we want to do quality assurance, we want to sit down and we want to identify the characteristics that we care about. We want everybody who's working together on the team to be aware of those characteristics. You want to differentiate between what are external and what are the internal quality characteristics. And you want to think about ways that these characteristics that you want may enhance each other versus they may work against each other. And then if they work against each other, you have to decide, how much of one thing you want and how little of another thing you're willing to put up with, right? Does your project call for the use of several different error detecting techniques suited to finding several different kinds of errors? Does your project include a plan to take steps to assume the software quality during each stage of development, right? Do you propagate through the whole process? Do you actually come up with a way of measuring the quality, right? Certainly you can have big tests that you run and you can see what the error rates is. Or you can have people look at the code and look at things like how long is the code and how long does it take to run. And you can actually measure things. And does management understand that quality assurance incurs additional costs up front to save costs later, right? This is the whole the saying is, quote, why isn't Bob programming, right? Sometimes management who doesn't understand, if you work at a company that's not a software company, the management might say, quote, why isn't Bob programming? He's sitting there, him and the other people are sitting there trying to, writing stuff on paper or on a whiteboard. Why aren't they programming? Well, they aren't programming because they're planning for success rather than just writing code and hoping they achieve success. All right, so hope that was kind of interesting. The bottom line here is if we want to have quality, I guess I'll stop this. If we want to have quality, we have to plan for it, right? We want to have quality in our code. And in fact, if we want to do our code quickly, if we want things to be done more quickly, we actually take time to do it right starting from the beginning. And this is why, I'm going to guess that some of you might have grumbled a little bit when I said, I want to see your designs. I want to see your system architecture, right? And this is because I was trying to get you to think about doing the design work first and then writing the code. Okay, well, next week's our last half week of class. And I know you guys are all working on your code. What you should do for today, you were supposed to turn in a second prototype, which I'm just going to look at. And so if you make sure your server's running, I would appreciate it, and I will look at those. And if there's any notes about that you want to give me as far as how to do it, send me those when you turn in the link to your running program. And good luck with all this.
Professor, so
Yeah.
are we supposed to make the server running like forever, or?
Right. If you leave your server running, it would be nice when you're not building. Obviously, when you're working on the code, you may need to restart it periodically, but try to keep it up so that over the weekend I can look at your code. And you guys understand how to do that, right? You can run it with if you do Node.js, the file, and then you do ampersand, it'll run in the background. And then if you log in to another session, you should be able to do a PS minus, I think it's AE, and you can see what processes you're running. And then you can do a kill and the process ID, which is the first number in the process list. The PS shows you the processes. And so you can kill your own processes. You can't kill somebody else's processes. Unless you're a super user, which I am. But you're not.
Pascal, I think you graded like the prototype too.
I did? Let me see.
Yeah, because like on Monday we present like our.
Oh, that was prototype 2. Okay. So
yeah.
we've already done, that's right. We've already done prototype 2.
Yeah,
I don't know what I was thinking. Yeah, you're right. I confused myself. Okay, good. So we graded prototype 2. So prototype, there is no more prototypes, right? So basically, what's important to know is for the final, we're all going to come to class, and each of you is going to do a complete presentation, not just a demo, right? You're going to show the architecture of the system, and you're going to talk about how the system was built. You're going to give a full demo, and you're going to talk about the lessons you learned about working as a team, about programming in these client-server environments, and about the challenges of building good user interfaces. So there's sort of a demonstrative part of this, there's sort of a documentation part of this, and there's a reflective part of it, right? Because part of what I want to know in your final presentation is I want to know that you've thought about, what you learned about the challenges of working as a team and what you might do different. And so that's whatever the day of the final is. The final is December 14th, 8:30 to 11:30 a.m. And so, and Jody and Caroline will be there again for that. All right. Well, thank you guys for coming to class. And I will see you later.